just going to review calorimetry problems. And the thing with calorimetry is there are so many different types of problems and different units that you can be asked for. And so what I want to do is, we already looked at the problems, but today I just want to review the different types and kind of just highlight to say, okay, if I see this type of problem, here's what I'm trying to do. Here's what I'm looking for. Here's the information that I need that's necessary in order to solve the problem. I also want to talk briefly about positive, negative, which is really important too. So, did your reaction release energy? If it released energy, then it was negative. If it gained energy, it would be positive. Perfect. Okay. So exothermic is losing and positive is gaining. But the problem is, when you have a calorimeter, something is going inside of the calorimeter, and what's going to happen is your reaction is going to, let's say that your temperature increases, okay? So you put your thermometer inside of your calorimeter and you check it, and the temperature rises. If the temperature rose, that means that the reaction did what? It's exothermic, the reaction released energy, okay? But what happened to the water? The water got hotter, it gained heat. Okay, which means that if you were being asked about the water would actually have an endothermic change. But you're typically not asked about the water. The water absorbed the energy and gained the energy. The reaction lost it. So what you're going to be asked is, what happened to the reaction? So what I want you to think is, if the temperature increases, if you see that your thermometer rises, the temperature on your thermometer rises, you're going to call that an exothermic reaction, even though your water was getting hotter. So people will always say, and typically it's AP Chem students, it's not the honor students, that get confused. Because, yes, the water did gain energy, but that's because the reaction lost it. Okay? So you're not going to have a lose without a gain or a gain without a lose. You're going to have both of them. So the question is, which one am I being asked for? Am I being asked for the water or am I being asked for the reaction? Typically, you're asked for the reaction. Sometimes you will be asked for the water, okay, for the sign of the water. Sometimes you're not asked for the sign. It says how much energy was released. Then they're saying, what's your absolute value, okay? What's the absolute value of the energy? So sometimes it's just how much energy was released or how much energy was absorbed. Then a lot of times it is just absolute value, don't add a sign, okay? But typically you will add a sign. It'll be a positive if the temperature dropped, and it'll be a negative if the temperature rose, unless they're asking you for the water, which typically they're not, okay? So let's take a look at some of these calorimetry problems. So we know that a calorimeter is basically made up of some insulated container on the inside, so some type of like styrofoam or something like that. And this is called a simple calorimeter. Even though this looks fancy, it's still called a simple calorimeter, okay? And then it has a cap, and that's where you're going to put your reactants in. So you're going to uncap it and drop your reactants into there. And then you have your thermometer, and the thermometer is not supposed to be used to stir. You do have a stirrer. There's a stirrer that you can kind of bob to make sure that everything that's inside is stirred well and you're getting one good temperature. So those are the parts of it. And we know that the major thing that we're recording with calorimetry is the temperature change. That is the one major thing. But let's just remember, if I took a huge pot of water and I had someone go to the middle of a lake in a boat, and I said, when we had our cell phones out, and I said, okay, on the count of 3, you're going to drop your pot of water into the middle of the lake, you're going to stick your thermometer into the middle of the lake, and I want you to check to see what happens to the temperature of the lake, okay? Another person is standing over at the edge, and you go, ready? 1, 2, 3. They drop the water in, and they stir the lake water, and they check the temperature. What happens? Nothing. Why does nothing happen? It's insignificant, right? So that heat, it spread across, and it made no change to the temperature, which means mass makes a huge difference in this calculation. So when we do delta H, we need to know what the mass is of the reactants inside of the calorimeter. If you have 50 milliliters, that's very different from having 100 milliliters. I know I exaggerated it with the lake, but I want you to think about that, okay? The mass here is the total mass that went into your calorimeter, all right? So if you have 2 aqueous solutions, which we have in lab today, and let's say you have 50 mils of one and 25 mils of the other one, then what's your total mass inside of the calorimeter? 75. 75 what? Grams. But I said milliliters. How is that grams? Milliliters are not equal to grams unless it's water. Perfect. And because we have aqueous solutions, we are going to say that since they're aqueous solutions, that a 1 gram is equal to 1 mil because that's the density of water. So we can say that whatever that mass is, that's the mass that's going in. But I don't want you to forget. Let's say that I have 50 milliliters of water and I end up dissolving 4 grams of a solid into there. What's my mass? 54. Awesome. Your mass, if you were to weigh it, the grams have mass. You need to incorporate that in. Okay? In a bomb calorimeter, you don't. The reason why you don't in a bomb calorimeter is a bomb calorimeter actually is supposed to have constant mass. Okay? So the mass that you put into the bomb calorimeter, that actually is not going to make a difference inside with your water. Okay? That's not going to make a difference to what's happening in your calorimeter. Okay. So now we're going to take a look at some of the problems to make sure that we have this down. Okay. All right. So in this problem here, we had acid, hydrochloric acid aqueous, being added to ammonia, which is actually what we're going to be doing in lab. That's one of the ones that we'll do in lab. And so what we ended up doing was we first figured out the MCAT. So we knew the mass. We knew the specific heat. It's of water because it's an aqueous solution. We knew our delta T. It's the temperature change that you get. And you want the greatest temperature change, okay? So you want, before you add it, what's your temperature of your, in our case, it'll be the ammonia that's inside of there. What happens to the temperature after you add it? What's the biggest temperature change, either high or low, okay? That's what you're going to be looking for when you're doing the lab. That's your temperature change that goes in there. What unit does this give me when I do M times C times delta T? Kilojoules. Awesome. Not kilojoules per mole. In order to get kilojoules per mole, you need to do kilojoules, moles, and then kilojoules per mole, okay? So we need to find moles first. And the way that you're going to find moles, if you have grams of a substance, that's great. So if I say that you had half a gram of some solid ammonium chloride, ammonium sulfate that you're going to put in, then yeah, and I want to know per mole of ammonium sulfate, for example, then what I can do is I can convert my 0.5 grams into moles, and then I can divide by that number of moles because I know the energy that was either released or absorbed, and then I know the moles, and I can just divide. But what if there is no mass in this problem? Then what you can do is you can use molarity times something to give you moles. Do you remember what it is? Molarity times liters. Perfect. Not milliliters. It has to be molarity times liters. And the reason why is if you use milliliters, your units won't cancel out. So just make sure that it's molarity times liters, and that's going to give you your moles. Now you have the kilojoules, you have the moles, and now you divide to get your kilojoules per mole. Okay? So that's one type of problem where you're given molarity and volume of 2 different solutions, and you're asked to find the kilojoules per mole, or the enthalpy change for that reaction. Okay? So then we did another problem, and this problem is very similar. The only difference, they gave you the volume and the molarity, another volume, another molarity. The difference with this one is that now our molarity and our volumes are not the same. They were the same in the problem before. So the question is, what if my molarities are not the same? Now, in this question, we were being asked for the kilojoules per mole of the product. So what we had to do first was figure out our delta H, because your delta H is going to give you what unit? Kilojoules. Awesome. Find that out. We do our M, our C, our delta T, same way as we just talked about doing the other problem. Now you need to find your moles. And the question is, do you multiply 3 by 0.100, or do you multiply 1.5 by 0.100? And we chose one. And it doesn't matter which one you choose, it's just that it's easier to choose one over another. Why is it that we ended up choosing the H2SO4? Why did we choose the H2SO4 and not the KOH?
There's a 1-to-1 ratio.
1-to-1 ratio. Awesome. 1-to-1 ratio between the H2SO4 and the K2SO4. So if we wanted it for the K2SO4, we know the moles of this would be the same. Okay? So as long as you know the moles of that, then those are the same. If I wanted water, I would use the KOH because those moles are the same. Okay? So then we figured out our moles. We did kilojoules, moles, and kilojoules per mole. Awesome. Okay. So then in this problem, this one's different because it's not a mixed solution. If the two are not mixing together and they're not dissolving in one another, now you need two MCAT problems. So that's an MCAT equals MCAT. And when you use that is, typically it's going to be a metal that's not dissolving inside of your water, for example, and you're trying to figure out the specific heat of it, you're trying to figure out the temperature change, you're trying to figure out, maybe you're being asked what mass it was if you knew all of the other stuff. So you have one unknown variable. And so you're going to use MCAT equals MCAT in that case, and they're not dissolving in one another. Okay, and that's a pretty easy problem to do. And the last one was a bomb calorimeter. Okay, now typically in a bomb calorimeter, they will tell you what the heat capacity is of the calorimeter. And they will give you the heat capacity in units of, they're just going to use C times delta T. And so when they give you the units, it would just be joules per degree Celsius. They're going to take out the mass. Okay, so that's going to be the only difference. Okay, so in a bomb calorimeter, typically they would get rid of mass because mass is constant. They already incorporate it into your calorimeter. In this problem, they didn't do that. We had to use our specific heat of water for this one, so they didn't give us enough information to be able to do that. So again, we did our MCAT the way that we normally would. The only problem was we were not looking for kilojoules per mole. We're looking for molar mass. And what are the units of molar mass? Grams per mole. So we knew the grams because the grams were already given to us right there in the problem. We knew the grams. We did not know the moles yet. So what we had to do was to find the moles. Was we used our kilojoule per mole right here. And as long as you could get rid of the kilojoules, then you have moles using a bridge problem. Okay? So once we figured out the kilojoules by doing an MCAT problem, then we could use the kilojoules per mole to solve for moles. And again, once you have that, you want grams per mole. So you find your grams, which we already had. You find your moles, which we found using delta H equals MCAT, and then just doing the bridge. And then now it's grams per mole instead of kilojoules per mole. Okay, so on the calorimetry worksheet, this should be pretty easy to answer. Bomb calorimeter problems, by the way, are used for combustion reactions for the most part, because if you try to use a simple calorimeter, it's not going to work because everything's going to melt inside of your calorimeter. Then down here we said, for number 2, for example, we're looking for specific heat, meaning that we're looking for C. So you're going to do delta H equals MC delta T, and you're looking for the specific heat. They give you joules here, so your answer will be in joules unless you change something, okay? So just take a look in this problem here. They're asking you for joules. So what do you think you're looking for in this problem if you're asked for joules? What in delta H equals MCAT are you looking for? The delta H. Awesome. Then it says, how many kilocalories is this? So just switch to kilocalories, and it's just, if you go up to the top, it'll tell you that there are 4.184 joules in 1 calorie per gram degree Celsius. So it's just 4.184 to 1, okay, for a conversion. This is looking for kilojoules. This one down here, notice, this is your 50 mils of a 1 molar mixed with 50 mils of a 1 molar. So what's your total mass in this one? 100. Good. It's 100 grams. Okay? So make sure that you get your mass right in this. They ask you to first calculate the kilojoules of energy, meaning you're looking for delta H. Awesome. Then it says, what's the enthalpy change in kilojoules per mole? So now you need to do the kilojoule, find your moles, doing molarity times volume, and then divide. Okay? So on this page here, I just want to come down to right here, where you're being asked for kilojoules per mole. I really like this problem a lot. So it says that you're burning a compound. They tell you that it's 2.50 liters, which you can convert to milliliters because then you can use grams. Awesome. Okay. And then they say that you burn 0.175 moles of this compound, and the temperature rises. So if you're writing delta H equals MC delta T, we know our temperature change. Because it's water, we can use the specific heat of water, depending on joules or kilojoules, whichever one you want. And then the mass, okay? The mass, we said, is the mass of the water in the calorimeter. We are not adding this in, because in a bomb calorimeter, it works differently. That gets put into a different chamber, and the mass is not included. It's constant mass, okay? So what goes in as your mass? The 2.50 liters, but converted, right? So it'd be 2,500, right? So that's what's going to go in as your mass. But when you get this answer, what are your units going to be? Either kilojoules or joules. Okay, but that's not what the answer wants. The answer wants kilojoules per mole. So now it says moles of compound A, not of water, of compound A. So guess what you need to divide by? The 0.175. Awesome. Sometimes they give that to you as grams, so then what you would do is you would convert it to, and then divide, okay? This is really important for the lab that you're doing today too, okay? Good? And then just make sure that you try all these problems out yourselves, and that way you know what you're doing. Okay? All right, and that's it for our review of